We often talk about optimization in manufacturing, but today we're looking at something closer to a revolution, a fundamental shift that lets manufacturers, just bypass an entire really painful step in the metalworking process.
You're talking about grinding.
Exactly. We're talking about hard milling. It's this technique of reliably cutting hardened steel that for decades has required slow, complicated, and frankly very expensive abrasive finishing. For this deep dive, we're pulling insights from some cutting-edge material science, looking at how precision tools are conquering these pretty extreme machining challenges.
Yeah.
At its simplest, hard milling is, well, the milling of high-hardness steel. But that definition of hard, that's where the real story is.
It really is. I mean, if you go back to the early days of modern metal cutting, the technological limit, that point where you had to stop cutting and start grinding, was incredibly low.
How low we're talking about?
The threshold for what was considered hard steel was around, say, HRC 30.
HRC 30, wow. I mean, that's barely considered hard at all in modern toolmaking.
Exactly. But that threshold, it's just been aggressively pushed forward. It climbed past HRC 40, then 50, and pretty soon it just blew past HRC 55. This isn't just, an incremental improvement. It's a complete game changer.
And today?
Today, it's common practice to reliably mill steel hardened all the way up to HRC 62, or even higher in some cases.
Okay, so let's unpack this. Our mission is to really understand the immense efficiency gains driving this shift, the brutal technical obstacles involved, and what specific innovations are making HRC 65 even machinable.
Right. We're dissecting this powerful manufacturing process from the economic incentives all the way down to the highly specialized technical requirements you need to actually succeed.
So let's jump right in. Why do manufacturers care so much? Hard milling requires a pretty significant investment in tooling, maybe even new machinery. So what's the fundamental shift that makes it all worthwhile? It's the complete elimination of the grinding operation. That's the prize. It just fundamentally re-engineers the entire process chain.
Okay, so walk me through the old way of doing things. Sure. The traditional workflow for, let's say, a high-precision metal part. You machine the component in its soft or maybe pre-hardened state. That part's relatively quick. Then comes the critical step, heat treatment.
And heat treatment, that's where things start to get complicated, logistically speaking.
Precisely. You need it for hardness, of course, but it often introduces dimensional deviations, warpage, or even surface defects like oxidation.
So to counter that, you have to machine in what they call allowances, right? Just extra material.
Exactly. Extra material just to account for those potential problems. After the heat treatment, you absolutely have to use grinding to bring the part back into tolerance and get that final surface finish.
And grinding is just notoriously slow. You're taking off tiny amounts of material at a time.
It's a huge bottleneck. It drags out delivery times and racks up labor costs.
So hard milling just sidesteps all of that.
Completely. If you can machine the material while it's already hardened, you eliminate that entire grinding stage. The cost and logistical savings from dropping a major operation like grinding are, well, they're astronomical.
And on the shop floor itself, getting rid of grinding also means you're getting rid of machine transfers.
Yes. You greatly reduce the number of times that workpiece needs to be set up and repositioned. Hard milling brings manufacturers closer than ever to that sort of holy grail of completing a part in a single setup.
Which for complex parts must be a massive deal.
Oh, for parts with complex geometries where multiple setups used to be mandatory, this boost in efficiency shortens delivery time and dramatically cuts the overall production cost. That's the ultimate payoff.
Okay, so we get the economic incentive. Now let's get a bit more technical. We've been throwing around HRC numbers, but how is this highly stressed material classified for cutting purposes?
Right. In terms of tool application, this type of steel falls under the ISO H application group. Industry standards, like the VDI 3323 standard, categorize steel with an average hardness of HRC 55 and above in this group.
But hard milling can start a bit lower than that.
It can. For general practice, you'd say hard milling applies to steel and cast iron that exceed HRC 45.
And this isn't just for steel.
Correct. We should note that the ISO H group also includes some really difficult to cut, highly wear-resistant grades of hardened cast iron, which can get up to hardness levels of HB 400 and higher.
This is where it gets really compelling for me. Cutting material this dense, this strong, it just sounds like a recipe for disaster for the tools and the machines. What are the major roadblocks when you're milling in that HRC 55 to 65 range?
Well, the material's high hardness dramatically intensifies, the friction and the cutting forces required. You are putting the tool and the machine under an immense constant mechanical load.
It's like trying to cut a rock with a kitchen knife.
That's a great analogy. The forces are just disproportionate to the material being removed.
And when you intensify that force, you're going to get a lot more vibration. You're talking about chatter.
Exactly. Chatter is the enemy of precision. This substantial mechanical load amplifies vibration, which in turn shortens tool life, sometimes catastrophically, and it just degrades the surface finish you're trying to achieve.
And what about heat?
That's the other big one. Increased cutting forces translate directly into intensive heat generation. This thermal impact can affect the tool's integrity and even distort the workpiece itself.
So with all those forces and all that heat, does hard milling only work if you have a massive, super expensive, ultra-rigid machine? Can a smaller job shop even get into this?
That is a critical point. It absolutely demands extremely rigid, high-performance machines to manage those loads. A softer, more flexible machine would just be destroyed by the vibration.
There's a pretty high barrier to entry.
There is, which is why manufacturers are so focused on using small machining allowances.
Smaller allowances.
Yeah. Because of these mechanical and thermal constraints, hard milling typically uses a much smaller depth of cut compared to machining softer material. It's overwhelmingly used for semi-finishing and finishing operations.
But can you use it for roughing it all? To remove a lot of material?
It is possible, but you have to use special techniques. Things like multi-pass cutting or high-feed milling methods, while always maintaining a very low machining stock per pass. The goal is always to manage that load and get the heat out without causing catastrophic tool failure.
So the process works if you can manage the load, but none of this is possible without the right hardware. The cutting tool choice has to be the key factor for success here.
It is absolutely the linchpin. The tool has to be designed to withstand temperatures that would soften normal steel, all while resisting forces that could chip a lesser material to pieces.
Where did this innovation even start? I mean, the jump from HRC 30 to HRC 65 didn't just happen overnight.
No, the initial major push really came from the die and mold industry, starting back in the 1980s.
Okay, that makes sense. Molds are high precision, very high cost components.
And the lead times were notoriously long. They were desperate to find ways to reduce the production time for new and restored molds. Hard milling offered a way to cut these pre-hardened components drastically faster than grinding could.
So that high-cost, high-precision demand really drove the technology forward. What principles did they borrow to make it work?
They adapted principles from high-speed machining, or HSM, but that required parallel innovations happening all at once. You needed better, faster machine tools, you needed advancements in powder metallurgy to sinter complex tool shapes, and maybe most importantly, you needed sophisticated coating technologies.
Let's talk about the materials themselves. What specific characteristics do these cutting tools need to handle that insane combination of heat and stress?
They need to meet extremely strict requirements for two things: high toughness, that's the ability to resist microfractures, and exceptional hot hardness.
Hot hardness. So that's the ability to stay hard even when it's glowing red hot.
Essentially, yes. It's the material's ability to maintain its structural integrity and its sharp cutting edge, even when it's operating at incredibly high temperatures, sometimes over 1,000 degrees Celsius, right at the cutting edge.
So what are the main players today? What materials are we actually using?
Coated carbides are still the workhorse. They're the most common material used globally for hard milling. For very aggressive applications, especially with indexable milling, you see a lot of cubic boron nitride, or CBN.
And for hard cast iron?
For hard cast iron, polycrystalline diamond, or PCD, is really the only option because of its extreme resistance to abrasion.
You mentioned those advanced coatings. We hear a lot about PVD coatings. What role do they play in making these tools so tough?
PVD stands for physical vapor deposition. It's a process where a very thin, very hard layer, often a ceramic or a metal nitride, is vaporized and then deposited onto the carbide tool.
And that layer acts like a shield.
It acts as a thermal barrier, exactly.
Yeah.
It dissipates that intense heat away from the cutting edge and dramatically increases resistance to both abrasive wear and oxidation. I mean, without these progressive coatings, milling at HRC 65 just isn't feasible, period.
Which brings us to the state of the art. If we focus on general innovations, what are the modern design principles that are pushing the limits of hard milling right now?
The modern focus is really on highly optimized geometries. paired with those advanced coating and substrate combinations we just talked about. We see this in both indexable and solid tooling. On the indexable side, where you have tools with interchangeable inserts, the innovation is all about load distribution and creating specialized geometries for complex 3D surfaces.
Oh, things like high-feed milling tools.
Right. Industry innovators have expanded their high-feed milling lines with special insert geometries that allow them to effectively machine materials all the way up to HRC 60.
What's an example of one of those geometry innovations?
A great one is the use of unique sort of bone-shaped inserts in some high-feed families. That design isn't just for looks. It fundamentally changes how the thermal and mechanical load is spread across the insert, letting it handle materials up to HRC 49 reliably.
And that's useful for repairs.
Extremely. They're very common in repair operations, like milling a repaired die surface after welding, which can have really unpredictable pockets of hardness.
And for the ultra-precision 3D finishing work.
For complex 3D semi-finishing, we're seeing single insert end mills that feature specialized burl and lens cutting profiles. These are game changers. They distribute the cutting force along a different, more favorable plane, and you get a fantastic finish on workpieces up to HRC 62. And looking forward, we are seeing indexable hard milling start to use specialized ceramics, which opens up some really promising prospects.
Okay, so that's the indexable side. What about solid tools, where you need maximum precision and rigidity? How are they managing the vibration that's just inevitable when you're cutting something so tough?
Vibration management is central to the design. Manufacturers have enhanced their solid carbide end mill lines using a concept of variable pitch and helix.
Meaning the flutes, the cutting edges are unevenly spaced.
Exactly. It disrupts the harmonic vibrations that cause chatter. You're basically using geometry to dampen the natural frequency of the entire machine tool system.
And what's the material science backing that geometry up?
These newer designs, for end mills in the 6 to 16 millimeter range, they use incredibly robust new carbide grades. Some of the leading grades feature a hard submicron substrate paired with a progressive PVD coating. That combination is just fantastic for resisting abrasive and oxidation wear.
So that's good for steel and cast iron up to what hardness?
You're looking at being highly effective in the HRC 45 to 60 range.
Okay, finally, what about the really tiny tools, the ones for micromachining? They must just snap under these loads.
You'd think so, but that's maybe the greatest feat of engineering here. Miniature end mills, some as small as 0.3 millimeters, now have these highly optimized geometries built for rigidity. They use ultra-fine, super dense carbide grades, which are also PVD coated.
And what hardness can a microscopic tool like that actually handle?
These miniature tools are being successfully used to machine steels with a hardness of up to HRC 65. Yeah, that ability to combine extreme precision with extreme hardness resistance just shows how far material science has come. So in summary, hard milling is an extremely demanding application. But the growing need for efficiency in high-value manufacturing has made enhancing these processes absolutely necessary. This raises an important question, though.
So what does this all mean? The key factor driving the industry forward isn't just about hitting a higher hardness number. It's about making the difficult significantly easier.
Right. It's translating those extreme technical limits, like cutting HRC 65 steel, into a reliable, repeatable process on the factory floor.
Allowing manufacturers to completely bypass the time and cost that's always been associated with abrasive grinding. We've seen the threshold of hard steel move from HRC 30 all the way to HRC 65 today. And that has fundamentally changed the landscape of metalworking. So consider this. What maximum hardness level do you think the next generation of coating and tool geometry technology will allow us to reliably mill? How high can that number go? And how will it change the definition of hard all over again?